So I think we'll be hearing Guillaume also talk a little bit about a similar or related subject. So we'll be able to have a lot more on insights on neuroscience and ML. For now, next up, we're going to be welcoming Bruno Rousseau and Pierre-Luc St-Charles for their presentation on one of the types of collaborative projects we do with partners, the AI applied research projects. It's one of the ways that many of our partners work with us more concretely on collaborative projects. More specifically, we will hear them on developing models at the intersection of deep learning and geoscience. It's an applied NRCan, so Natural Resources Canada, and AMLRT, Applied Machine Learning Research Team, project case study. Bruno and Pierre-Luc obtained their PhD in 2008 and 2018 respectively. Bruno studied condensed matter and material physics and then worked as a data scientist in a consultancy firm. And Pierre-Luc studied computer vision and image processing and then worked as a postdoc in Montreal-based Research Institute. Both joined Mila's applied machine learning team as research scientists in 2019 and have since worked on geoscience projects with the team. So Bruno, Pierre-Luc, the floor is yours.
Good morning. Thank you for that great introduction. So today, Pierre-Luc and I will present our team here at Mila, and we will do so in the form of presenting a project that we have ongoing with NRCan. So first, we'll introduce the Applied Machine Learning Research Team, which we like to call AMLRT. It's not a city in the north of Canada, it's our team. Then we'll discuss what a typical pipeline looks like when we have a project in collaboration with a partner or a client. And then we'll dive in a little deeper on that project we have with Natural Resources Canada. Their expertise that they bring to the table. We'll summarize a little bit the data that they brought to the table, what our mandate was, and the outcome of that project. So first, our team. We are a team composed of 18 research scientists. We are led by 3 managers with a combined experience of over 40 years in machine learning and deep learning. We cover a wide range of machine learning and deep learning expertise. Of course, natural language processing and large language models, which are all the rage these days. We also have extensive expertise in computer vision. But what is perhaps a bit unusual is we also have a diversified team with expertise across the board in perhaps more unusual domains for deep learning. So whether it's fraud detection or time series forecasting, the types of topics that are often of critical importance for companies, but that are perhaps less touched upon in academia, we have a lot of experience with these kinds of projects.
So one thing we could also highlight here that's actually fairly interesting is that everybody in our team has a totally different background in a way. We have physicists with us that are helping us try to deal with problems that typically just as computer engineers and computer scientists, it might not be easy to solve them, but this is actually something that's actually very useful, unique, and actually required for our type of work, because we work at the intersection between different domains. And in this intersection, we need to have a wide variety of perspectives to try to tackle each problem.
So what are the kinds of services that our team can offer partners? On the one hand, we have our collaborative research projects, which are really hands-on. Typically 2 team members, led by one of our managers, will really get their hands dirty and produce a full-fledged solution. We can work with confidential data if need be. We can leverage the computational resources of our partners, whether they be on-site or in the cloud. We like to first, of course, identify what is the highest value problem that can be tackled with a partner. And we can really tackle difficult and niche problems. As was alluded to by the previous speaker, it's often necessary to tailor-made a solution to a complex problem. So that's really where our team shines. A key point in the projects that we take on is the relationship that we build with domain experts that are employees of our partners. It's really, really important that we have ongoing conversations with these domain experts to make sure that the project stays focused on the highest possible value, right? We are very knowledgeable across a wide variety of fields, but still we must have input from domain experts to make sure that we're headed in the right direction. Our goal also is to transfer the machine learning knowledge that we've acquired throughout the project to the clients. We are not product vendors. Our goal is not to just create a solution and walk away. Our goal is really to transfer the knowledge and the solution so that the partner can own it and leverage it in an ongoing fashion. Our typical projects, since we're talking about complex topics, typically it's 12 to 14 months, and there is access to funding to cover a significant part of the cost. Another aspect of what we offer is more consultation or training. So these typically will last over a 4 to 6 months period, and one team member will offer what we would call more like a coaching or service, offering about 25 to 50 hours to a company. So we support industrial research and development projects where what we offer is really guidance, tips, and making sure that the protocol established in collaboration with the company is robust and sound.
Well, one thing also that we could highlight that's actually interesting here is that our team does not focus at all on productization. It's something that's actually fairly unique. So we stick to proof of concept development. And when it comes to actual productization, we assume that the knowledge we transfer is really the scientific part for maintaining the experiments, developing new models, things like that. But in the end, we do rely on clients to be able to productize their own models.
So today, we will focus on our project with NRCan. We'll briefly dive into the project pipeline that we put together in collaboration with our partners. And we'll summarize the data that was available for this project and what our mandate was. So our collaborators are affiliated with the Geological Survey of Canada, which is a branch of Natural Resources Canada. Funny fact, the Geological Survey is older than the country itself. So on an unrelated topic, the research scientists we work with there have a lot of experience. And so they really are world level experts in geology and seismology, but they wanted to know if we could bring in some deep learning and machine learning to their workflow to improve the efficacy of their work. And so when they came to us, they really had this one data set that's centered around the Lalor mining camp, which is a mining camp that's on top of a so-called volcanogenic massive sulfide ore deposit. So that's basically a gold and zinc and copper mine. And the data that they have at this site is pretty unique, pretty unusual. On the one hand, they have seismic data represented by the image at the bottom of the slide there. So essentially, this is obtained by using essentially dynamite to create shock waves in the earth and measuring those shock waves at the surface of the earth with little sensors. And the imagery that you can extract from these kinds of measurements is akin a little bit to an echography, right? When a doctor uses ultrasounds to visualize a child in a mother's womb. So it's indicative of where the interfaces are, where we go from one type of rock to another. But as you can see, it's a pretty ghostly kind of source of information. It doesn't tell us exactly what's there. It basically tells us where there are changes or interfaces between rock types. They also have access to all of these borehole data, which are essentially carats dug deep underground. And as you can see here, these spaghettis kind of tell us a little bit the kind of rocks that are there. So every different color that you can see on this image corresponds to a rock type, red being the ore, right, where the money is. And so what we end up with this data set is a sparse 3D point cloud of rock class types. And it's not very uniformly sampled. Of course, they dug closer to where they initially thought the ore would be, and it gives us incomplete, noisy information about what's under there. So when they approached us, they were wondering, can we use this information in order to create basically a map of the underground? So the inputs would be the seismic data and some of the borehole data in order to produce basically a complete mapping of what is the rock type at every point underground around this mine. To be clear, the image that you can see at the bottom of the slide there is the kind of models that they can already produce by using only the borehole data, right? It's basically a sophisticated interpolation. That approach does not leverage the seismic data at all. So the real question is, can we leverage this seismic data in order to produce maps that are even better than what they can already do? And that could be a very interesting question to answer. It can have very important economic impacts because digging these holes is extremely expensive. Creating a seismic survey is also expensive, but for the price of 1 or 2 extra boreholes, you can have a seismic survey. So if it's a game changer that can really help understand what's underground, then there's potential economic benefits in the way of reducing the number of boreholes that are necessary. So we talked with them, and of course, we wanted to propose, develop, and train models to do this. There were 2 aspects. First, to begin with, we started with a simpler task, and we helped them with the data pre-processing using computer vision-based approaches. And then we wanted to tackle this specific problem. Can we improve the map of the underground by leveraging that seismic data? So now we can say a few words about our pipeline.
Sure. So overall, one thing I'll probably try to highlight first is that this pipeline is essentially just a high-level description. Every project is going to be fairly unique, and we tend to iterate and maybe jump between steps a lot. It's really on a project-per-project basis. But for now, let's say this is an overview. So these are the different steps. We're going to go through them one by one and essentially try to highlight some of the key aspects that made the NRCan collaboration project unique. So first, the prerequisites. Of course, this is a machine learning project. Before we even step in, we need to make sure it's actually something we can solve, or at least we can provide some help with. The first step is really trying to identify whether the data itself is in sufficient quantity in order to be analyzed or processed. This is something that's really right off the start. In the first 2 to 4 months of the project, we need to figure out what sufficient actually means in this context. And this is, again, very unique for each project. For NRCan, it was actually quite challenging to figure this one out, but I'll get back to that in a moment. Next, the annotations themselves must have a decent level of quality and consistency. This is even just at the annotator level. If we provide the same data to 2 experts and they give us different annotations, there might be some trouble there. So this is something we really need to consider before we get started on the project itself. Then we must have access to the domain experts directly. We do not want to be in the dark in our own sandbox, trying to prove ourselves right, doing things that are illogical. So this is actually quite necessary. And in the end, the project itself must be a good fit for machine learning methodologies, let's say. There must be kind of a methodology that we can set up and try to use to actually provide interesting results. So for NRCan itself, the first thing we can note here is that we only had access to data for 1 mining camp. One thing that's interesting is we had synthetic data, which made the project actually doable, but we only had 1 mine. So in terms of trying to say, oh, we're going to apply our models across Canada and we're going to discover amazing minerals, maybe not. So this was something we needed to consider right up front. And then also one thing that's very interesting to note here is that the seismic data is noisy and incomplete. It does not give us a full picture of what's actually underground. It is still linked to rock unit interfaces, but it is something that is fairly fresh in the geology literature. It's something that was proposed as, hey, we could use this, but it wasn't totally 100% demonstrated in the past. So our ultimate goal here was really to try to do better than what geologists were already doing with fewer boreholes by leveraging the seismic data itself. Ideally, they just wanted a second opinion on the interpretations that they already had, so any kind of results were interesting to them. The next step is actually quite important for our own work. It's the domain understanding part. So we can split this into 3 steps, essentially. It's first, we do data analysis. So data analysis, the first step is really, okay, you told us the annotations are consistent and everything, but now we're actually going to go and dig into the data to make sure that's true. And in this case, it's really all about trying to figure out where the issues are. Next, we're going to actually analyze the distribution of the data. So in this case, try to understand how seismic data works, because we're really not experts in that. At least I wasn't. And in the end, we also want to identify anomalies and biases in the data so we can actually figure out the problems that we might encounter on the road to what we actually want to do. So for NRCan, the first thing that we can highlight here is that we did find numerous issues with the labels that were provided to us, especially in the seismic pre-processing part of the project. And in the coordinates that we had for the 3D boreholes, so the spaghettis in space, this was actually quite challenging to figure out that there were issues. We had to do a lot of back and forth, but this is something that's drastic and super important to figure out before we start working. And also, one thing that we wanted to do was try to figure out that seismic data is indeed correlated with rock unit interfaces. This is something that was quite fundamental, and Bruno was quite the expert in doing that. There was a lot of math involved, and I'm quite happy it was there for me. So in the end, the next step for domain understanding is really trying to understand what is typically proposed in the target domain. So this really goes through first, what do experts consider as their own baseline approach? What is their standard butter knife when they want to tackle this kind of problem? Then we need to figure out what kind of valuation setting are they typically using to say like, oh, okay, my approach is better than yours. We need to really understand that, because it's never as clean as in machine learning where you have nice data sets that are prepared in labs. Then we need to really try to define what can be considered as an improvement over baselines. And this is something that's actually quite unique in the case of NRCan. So first, the baseline approaches for this project were Gaussian processes, so Kriging models. Again, I'm very glad I have Bruno with me, because these models are quite funky. And in the end, just understanding them and trying to compare with them is quite challenging. Next, one thing that's very unique also is the fact that we have a single mine. We have data for a single camp. So we're not going to be trying to generalize our models across Canada. So how do we actually evaluate? Well, it's within this mine. Can we evaluate or try to generalize across space for this one survey site? And that's our ultimate goal. And then finally, as I said before, any kind of results that are usable as a second opinion for something that might be surprising to an expert is already something that's an improvement, a potential improvement, because they will go and dig and verify.
One thing that we learned speaking with them about this particular topic is that each mine is unique. It's its own little thing, and they will spend years and years and years in analyzing the same site. So there's immense value in providing a second opinion. So that's not something that we came to the project already knowing. We discovered that through our discussions with our counterparts at NRCan. They were very happy with just being able to produce anything on this one site. No need to try to predict for 50 mines.
Yep. Next, for domain understanding, essentially, we're going to dig through the literature, both in machine learning and in the domain itself, to try to understand first if there are tasks or benchmarks that can be used that have similar inputs and outputs. And then we're going to try to figure out if there are methods or techniques that can help with specific challenge related to the project. In this case, one thing we figured out was, okay, well, the kind of task that we have at hand is essentially semi-supervised binary image segmentation combined with some label propagation. This is something that we found that was linked maybe to, in microscopic imaging, cell segmentation. There was a few links there. So it's the kind of literature that we're going to go look through. And also for the techniques and the methods that can help us deal with this particular problem, domain adaptation was actually something that's quite needed in this case, just because we have synthetic data and we're going to try to apply it to real data. So yes, quite challenging. So the next step in our pipeline is really going to be to try to formalize the problem itself. So the first step in that is really trying to build an experimental protocol. So this is really just a high-level methodology for what we're going to do. First, we're going to try to figure out what's going to be ingested for our models. In this case, we do have funky data. It's images and sparse point clouds. So this is funky. Then what we're going to predict. Finally, how we're going to split the data. And really, there's a fourth step. It's trying to figure out how we're going to evaluate the actual predictions. So for NRCan, as I just mentioned, it's seismic reflection images and borehole data. So there's two modalities there. We already know our models are going to be at least multi-model. Then at least the predictions are just arrays. So that's good. It's arrays of class labels. The split itself, it's interesting. We only have one site. So essentially the boreholes or the spaghettis, we're going to split into different sets and try to have an expert do the actual split so we can evaluate based on scenarios. And finally, just use classic classification metrics to do the evaluation. Next, in the problem formalization, it's really trying to figure out a research plan for the things we're going to work with in experiments and try to improve baselines upon. It's first, how will the model learn? Then it's the kind of model architecture we'll use. And finally, it's the kind of training approach. So there's a lot of variety there. This is mostly where we're going to contribute new state-of-the-art machine learning knowledge. So for the NRCan project, it was really, okay, well, we'll just use classic classification losses because, again, there's nothing fancy in doing classification. But for the model architectures, we're essentially in the end combining convolutional neural networks with graph neural networks. So there's some funkiness there. And we're going to use self-supervised learning to do pre-training of our seismic encoders and then try to do domain adaptation fine-tuning. So this is really where things are going to be a little bit more complex and off-the-shelf solutions that we can typically find in the literature. And this is where the expertise of our team really shines. For the experimentation itself, again, now that I will skim over this fairly quickly because each solution is really project specific and we don't have time to go really dig into the details of the NRCan project. But the first phase that we did, as Bruno mentioned earlier, is the seismic pre-processing. So this is a fairly standard computer vision pipeline where we take the input raw data and we do a little bit of processing, do predictions, and we come up with a result that's actually fairly interesting for our collaborators already. The second phase of the project was using the seismic data that's already been processed. We're going to try to detect the actual interfaces between rock units. So where rock A comes in contact with rock B. This is something that we started doing with synthetic data first, where we could have the full ground truth and everything that's underground. And then the third phase of the project is really trying to do label propagation. So knowing where the rock interfaces are and having the spaghettis floating in space, we're going to actually propagate the rock unit labels across the space and try to map out the whole mining camp. In the end, yes, this is still quite a difficult step, even though it's one that might be somewhat simple to explain. So now finally, in terms of reporting, each project is fairly unique again and again and again, but these are the main components of what we provide in terms of reporting. So a final report that provides a full description of the data analysis, methodology, experimental results, observations, everything that we can think of is going to be in a final report. Then we have a summary of ideas for future research, potential improvements and limitations. This is something that's actually quite important because we want our clients to really know what the limitations of the solutions we're bringing to the table are. Next, in terms of code, this is something that might also differentiate us from maybe more academic, let's say, contributors. It's that we will provide standalone experiment framework with a lot of latest like tools and modern tools and everything. And this is going to be high quality code with documentation, testing, all kinds of stuff. So it's going to be good and well done, along with configuration files that can allow you to retrain any kind of model and everything. For the models themselves, I'll just mention that we're going to have checkpoints that are easy to use and things that are actually tuned to be easy to use and good for your compute resources. So now, in the end, for the NRCan project, this is something we spread out over 2 years. So we did deliver a lot of things at the end. So for the project outcome for this actual project, so our hands-on work actually identified many challenges, including the fact that synthetic to real data adaptation is super challenging. So we actually had to develop a lot of new ideas in this case. The rock unit interfaces detected are always going to be imperfect, and this is something we have to deal with, but the uncertainty is part of the challenge of this whole project. And in the end, also doing label propagation with volumes that have 50 million voxels, it's really not easy. And yeah, so this is still ongoing work. We're tackling a lot of ideas in domain adaptation graph neural networks. If you've ever heard of problems that seem somewhat familiar to this, let us know. We'll probably recycle some ideas. And in the end, we did get a publication in NERC's 2021 workshop for a physical sciences workshop. So that was actually interesting because this publication has already been reused by many people trying to build and benchmark their own methods. And we're currently working on a journal extension for this. So this is it. If you're interested in collaborating, don't hesitate to contact us. We can definitely chat. It's always great just hearing about potential project ideas and everything. So thank you.
Thank you.
Thank you very much, Pierre-Luc and Bruno. It's interesting to hear that there's really something at Mila, and a lot of people share that, but Danilo mentioned it, and you guys mentioned it, the variety of disciplines that we can kind of cover, that we have domain expertise of, or that we can talk with, is really interesting. So don't hesitate to send us a message, especially for the types of projects that they do. It's great to hear from them every time. And yeah, so thank you, Bruno, and thank you, Pierre-Luc. So we'll be going on a small break. We'll be back in about 20 minutes. So there's still coffee, still pastry on the other side, and we'll see you in 20 minutes with Guillaume. Thank you very much.